we will use a simplified model. Let's say we don't need to put the noise, and we simply consider of starting from a received waveform like this. Note that now we are in the continuous time. That is basically the basic difference today compared to the material that we have seen in the past classes. The basic difference is that we start from the continuous time signal. Okay? And now we study a piece of the passage between the continuous time and the discrete time. That is, now you have to sample this signal. And sampling must be properly synchronized. Okay? So basically, what you have is the sequence, the G, and then the sampling at KT. The point, this is Y of T. This is the source. And this can be, for instance, the KIM or the PSG, the input modulated sequence. This filter represents the cascade of transmit filter, channel, receive filter in the continuous time. Okay? Now we must pass to the discrete time, meaning that we must sample the signal with a rate that is equal to the symbol rate, and with a phase like this. Or the minus, the plus, sorry. Okay. No, the minus, because we must put the T here to cancel here the T0. This is a delay which is unknown. That is, as in the carrier recovery, what is unknown is the phase theta of the carrier. Here in timing recovery, we assume that capital T is known, while T0 is unknown. And by now we treat T0 as a random parameter. That is, we assume that T0 is fixed. It is not subject to random walk. Then of course we can make our study more, let's say, accurate by introducing some other model for the T0. But the first approach is this. The symbol frequency is known. The timing parameter T0 is unknown. This is like the frequency of the carrier, the phase of the carrier. Okay? That is, you must put here a waveform like this, where this is capital T and is known, and you must find the timing. That is, where is this rising edge compared to T equal to 0? This will be our T0. Okay? I must catch this information by signal processing on Y. Okay? This is the goal. Specifically, my objective is to get from Y, that is I need a subsystem whose input is y. Here there is some signal processing. And at the output of this system, I want a sinusoid like this. And then I pass it through a rectifier and get this clock. This is called the clock. You see a sinusoid like this is T0. This is, sorry, minus T0. That its rising edge is at t equal to minus a T0. So we could draw this in this way. T0 with the minus sign. And then zero crossing again after capital T seconds. Capital T is known. Okay, this is the objective today. What should we put here to get from y of t this result? This is the objective. Having this, we pass it through the rectifier and we get our clock. Okay? And use it here. So the basic, we don't have that. We cannot rely upon that. Simply looking to y, we must understand the T0. How to do this? Well, the basic observation is the following. Y of t is not stationary. It is a cyclostationary. Cyclostationary means that its statistical properties are periodic, and in this case the period is capital T. Or to see this, look to the I diagram. So you know the I diagram, and consider binary transmission. The I diagram is what you see on the oscilloscope. And it looks like this. Suppose by now that we have the Nyquist criterion that is satisfied, and these are the transitions of y or t in time, and this is capital T. You can immediately see that this signal is not stationary. For instance, at this time instant, it takes only two values, +1 and -1. So the probability distribution of y in this time instant is like this. Now, look to what happens here, exactly in between two eyes. here you have a probability density function of y that is much smoother. It will become similar, let's say, to a bell. And you have a probability of crossing the zero, for instance, that here you don't have. So this means that the statistics, the probability density function, and therefore maybe also the moments, the mean, the second order moment, are different here and here. So the signal is not stationary, because for a stationary signal, the statistics of the signal is the same, independently of the time instant where you get it. Or this also means that it is not completely random. Okay? You can guess something simply by knowing the time instant. And also, this statistics is periodic. That is, if you move your attention to this time instant and make a lot of realization, you will find the same distribution as here. And if you look here, you find the same distribution as here. So it is not stationary, but if you take a sampled version of y with sampling delay capital T, then the discrete time, the sampled signal is stationary. And this is true whatever is the sampling phase. You can say this by and this is true for anything. It is a sort of definition of a periodic signal, but now you use the expectation operator. For a periodic signal, you have that y is equal of y. This is periodic and deterministic. Deterministic and periodic, okay, for any t. For any t, you have this, and this is the definition of periodicity, with period capital T. This is what happens with a random signal. You make any transformation of the random signal, take the expectation, you repeat the operation, but now transform, in place of y of t, transform y of t plus capital T, and take the expectation. If this is true for any t, then the random signal, random y, is cyclostationary. Okay? Which is, cyclostationarity is a property that is similar to the periodic property, but it applies to random signals. Any, for instance, moment, the first order moment, the power, and blah, 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 you take the expectation of any transformation. So, for instance, any moment is periodic. When this happens, then you say that the random y is cyclostationary. Now we can leverage upon cyclostationarity for getting our result. The basic observation is that if we make the expectation of y, it is a zero everywhere. So actually y is stationary for the mean. It is a special case of this, you see? This is a special case. It is always the And so, let's go on. What about this? For sure, we will have this relation. Consider a baseband signal, a real signal. Don't care of the complex signal. Consider a baseband signal. For sure, we will have this. If we make the power, compute the power, computing the power in this way means we consider a large set of realizations of y, and then we look to one time instant, compute the square for each one of the realization and make the average. Okay? Then we make the same after capital T seconds. Well, we see that these two are the same. We get the same number. So the mean value of the second order moment is periodic. Also this one is periodic, but is trivial because it is constant actually. This equation says that the mean value of the second order moment is periodic. This means that if we make a square and then an average, we get the mean value of the second order moment. And this is periodic, with period capital T. How is the spectrum of a periodic signal with period of capital T? Well, it contains a sinusoid at frequency 1 over T, which is exactly what we are looking for. So basically what I'm saying is make the square and take the mean. That is, put a low-pass filter. Because as usually taking a mean in the practice means put a low-pass filter. At the output of the low-pass filter, you will find the sinusoid of period capital T, which is exactly what we are looking for. Then you can find also other things. Because actually you will make the mean of y, not of the expectation of y. So really what you will find after the filter is the expectation plus some other things. For instance, other sinusoids or other component, other random components, due to the fact that this is an ensemble average, while with the low-pass filter you make a time average. Okay, so to get exactly the period, you should have an infinite number of realization. Now, let's go on along this way. Let's see what happens by rising to the square this one. Or to see this, let us assume that g of t is something like this. This can be an intuitive way to regard the operation that we are going to do, with a duration that is much smaller than capital T. This is a special case of this one. Okay? Now, consider a sequence. This is G. T. Consider a sequence Y of impulses with random amplitude. For instance, +1, +1, -1, +1, +1, and so on. -1, -1. Do you agree? This is an example of realization of Y with a G like that. Okay? Now take the square. What happens when you take the square of that Y? Y to the square. You will get this, 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 this. You see? A periodic signal. exactly a periodic signal. And then, if you look to the spectrum of this signal, you will find the zero frequency, which is the power, the expectation of y to the square, what is the average of this y to the square, that is the average power of y, and then a sinusoid at fundamental frequency 1 over t, which is what we are looking for, plus other sinusoids at frequencies that are integer multiples of the fundamental frequency, a periodic signal. Really, what happens is that in the general case where the g of t is not time limited, there can be some randomness. Yet in this case, in this special case, the square of y is a deterministic signal. Okay? Now suppose that in place of +1 and -1, you have also the +3 and -3. So, in that case, you will have realizations like this. 3, 1, -3, -3, -1, +3, and the square at that point will be no more a deterministic signal. It will show some randomness in the amplitude. Okay? This is no more a deterministic signal. It has some randomness. That is, it is a mix of deterministic and random signal. Because, you see, I expect the peak at given time instant, and this is not a random behavior. I know that the peaks are here, 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 and so on. Simply I don't know how large are they. Also, I know that in this time range, time window, the signal is 0. And this also is deterministic, because it always happens that it is 0. In time range, that are always in the same position. Okay? So that signal is a mix of randomness and deterministic behaviors. So, in the case of a purely random signal, you will have a distributed spectrum, a dense power spectral density. In the case of a periodic signal, you will have only spectral lines, Dirac deltas. In the case of signals that are a mix of the two, you will find both spectral lines and smooth spectrum. Now, let's make this picture a little bit more complex. Suppose that the impulse response is not time limited. Then there will be some overlap between the two. And this overlap will be in some sense random, because it will depend on the random amplitude sequence. This will add other randomness to the signal. Okay, but anyway, the very concept is that what we expect by rising to the square y, what we expect is to find a signal whose power spectrum is a mix, is the sum of a distributed, a continuous, a smooth spectrum and spectral lines. Spectral lines due to the cyclostationary nature of the underlying process. Okay? So with fundamental frequency at the frequency that we are looking for, 1 over t. Let us analyze this. Analyze this. We write simply this. can always write a random singular like this. A deterministic part that can be 0 plus a random part. All you need to write this is to specify that the expectation of this noise is 0. Do you remember? We already found this approach in the random gradient. We write the random gradient as the sum of two parts. A deterministic part, which is the part that drives us to the minimum, plus a random movement, a random part depending on the randomness that are in the error samples. And here it is the same. We write the square as the sum of two parts, the expectation of the square, and when you write this, what remains as a zero min. Okay? Simply because if you apply the expectation operator to this equation, you have that the expectation of y to the square is the expectation of y to the square plus the expectation of eta. And so the expectation of the expectation is the expectation, and therefore the result is that the expectation of eta is a 0. It is simply a way of splitting the deterministic and the random part of a signal, which is a mixed y. Like y to the square is. It is a mixed y. Now let us give a name to what we want. We want this because here there are the spectral lines. So we call this Z, the expectation of y, and we study Z. This is the expectation of y. Now put in place of y that writing it there. Do you know what is the square of a sum? Formally speaking, this is a sum, this is the square of a sum. To the square. Do you know how to write it from a formal point of view, a purely mathematical notation? How to transform the square? Well, it is easy. It is the sum of a sum. So this is sum I, sum k, ai, ak, g with the I, and G with the K. Okay? You can check this. It's easy to check. It is the sum of a sum. Now we put the double sum inside the expectation and compute the expectation. Sum I, sum K, AI, AK, GI, GK. Okay? Is everything easy and smooth? Someone of you can compute this expectation now? What do you need to compute this expectation that you don't know? Some assumption about the randomness inside the expectation. G, as usual, is the response of a filter. So it is deterministic. No problem with G. Where is the randomness? The randomness is here, into the symbols. So, the sum, the double sum can go out of the expectation because of linearity. So this can be written as the sum I, the sum K, G, which is non-random, so also G can be brought out of the expectation operator and then multiply by the expectation. Now it's easier, is it? Now we must make some assumption about the symbol sequence, a statistical assumption, and substitute our assumption in place of the expectation. What do we assume usually with the symbol sequence? Well, we assume that the expectation of AI is 0, and that the expectation of ik is 0 for I that is not k, that is, they are uncorrelated. And, I don't know, sigma a to the square for I equal to k. This is the typical assumption that we make on the data sequence. The data sequence is IID, independent and identically distributed. And independency means also uncorrelation. Then, of course, when I is equal to k, we have the square, and so we have the variance because the mean is 0. Okay? So if we put the assumption here, what remains of this double sum? Well, it remains only the terms with I equal to k. Yes. All the other terms disappear. And so we get the result, sigma a to the square by the sum over k from minus infinity to plus infinity of g to the square t minus kt plus t0. Is it? Okay? Are you following me? Are there questions? No question. Now, please, characterize z of t. It is characterized in the usual way, continuous, discrete time, periodic, aperiodic, random. How is a z to your eyes? Look there. Is it continuous time or discrete time? Of course it is continuous time. Z of t, I'm writing the z of t. It is a continuous time signal. I say, well, I would write zk, something like that. Is it random or non-random? Non-random. It is an expectation. The expectation is not random. We always assume that we know the statistics of the signal. So we know the expectation. We know the density, the probability density function, as well as we know all the impulse responses of the filter. So it is continuous time signal. It is deterministic. Is it periodic or aperiodic? It's periodic because it is the repetition of a basic impulse. The basic impulse is g to the square of t plus t0, and then by this sum we make the repetition and then the sum of a basic impulse. So this is a continuous time, deterministic and periodic signal. How will be the spectrum of Z? That is the Fourier transform of Z. It will be a spectrum made by spectral lines, a sum of Dirac deltas. The first one at frequency 0, the second one at frequency equal to the inverse of the period. What is the period of the signal? T. So the first spectral line will be at 1 over t, what we are looking for, and then other spectral lines. So now we can put a filter after the square to get the first spectral line, and then we look to the phase of it and to add a delay to make it phased with what we want. So let's study the phase of, let's say, before studying the phase, let's study the spectrum of that Z. And to do this, it is useful to write W equal to the basic impulse. Let us use this, no, sorry, not W, V. And write Z as the repetition of this basic V. Oh la la. Sorry, I must answer. Sorry for this, but it was mandatory for me to answer to this call. So audio off. Okay. Okay. Simply we substitute, and then we say that the Z is the repetition with period t of the basic V and with time offset t0. If this is V, then the Fourier transform of V will be sigma a to the square G convolution G. This is a constant. This is the product of G with itself. And the product in time is the convolution in frequency. Okay? Basic property of the Fourier transform. Now the Fourier series of Z, so this is the basic impulse, and this is the repetition. To get the spectrum of the repetition, simply it is enough to sample the Fourier transform of the basic impulse. Do you remember this? So 1 over t because of sampling, the sum for k from minus infinity to plus infinity of V, capital V, at k over t. This is the sampling. This is the effect of the time offset. It becomes in the frequency a complex exponential, and these are the Dirac deltas. So that is the Fourier series of Z. It is the sum of Dirac deltas. The weight of the Dirac delta is the basic impulse, the Fourier transform of the basic impulse at k over capital T, and this is the delay in time, which becomes a complex exponential in the frequency. Now in place of V, we substitute the convolution, and so we get sigma a to the square divided by capital T, the sum for k that goes from minus infinity to plus infinity, the complex exponential to pi k T0 over capital T, the Dirac delta, and the convolution. D nu. This is the convolution between G and G at frequency k over T. So G of nu dot G of f minus nu, where f is equal to k over T because of the product with the deltas. So we need to know the convolution only at the frequency where there is the delta. Outside that frequency, the delta is 0. Okay? This basically is an exercise of signal theory. So periodic signal, make the square, that is the convolution, take the expectation and get a deterministic signal, and blah, blah, blah. Substitute, put the delta, the delay. It is an exercise in signal theory. Okay? Now let us put some assumption on G to study this convolution. Typically, in typical design, G of f is equal to 0 for f in modulus that is greater than 1 over t. This happens, for instance, with all the members of the family of the Riemann cosine impulse frequency responses. It means that G of f, if this is 1 over t minus 1 over t, G of f can be this, the rectangle, the ideal rectangle. It is band limited, and the bandwidth is 1 over 2t. Or it can be this, with a little bit of roll-off, or this, the roll-off equal to 1. This is the family, for instance, of the Riemann cosine. Do you know it? Okay, we assume that it is band limited. Band limited to 1 over capital T. So this integral is 0 for k modulus greater than 1. So let's look to what inside the integral. It is G by flipped, frequency flipped, frequency reversed version of G plus a translation. You see? This is a translation in frequency. So if this is G of f, how is G of f minus, or better, 1 over t minus f? This will be 1 over t, and this will be G of f, 1 over t minus f. Is it? Translated version. If the G of nu is even, this operation, the minus, there's no effect. Because the two are the same, but the translation remains. Okay, and so this will be G of minus 1 over t minus f versus f. This is 1 over t. Okay, do you see? With the minus in front. And then, let's go on. Let's look to G of 2 over t minus f. Well, this will be centered on 2 over t, like this,
根本没有交集吧
okay?
只有可能是
Again, an exercise in signal theory, the second year of the first level degree. Now make this product between this and itself when k is equal to 0. Okay, it is g to the square. And so the integral will be non-zero. Make this product with this one. Well, they will overlap a little bit. Well, the picture is not so beautiful. I draw another picture with where I can highlight g of 1 over t minus f, and this will be g of f. Like this. Okay? And then make the other product. G of f, 1 over t, g of 2 over t minus f. And this is g of f. What about the product between these two? The product between these two is a 0.
0
While the product between these two is non-zero because they overlap in the Roloff region.
yes
In the limit, if we use the ideal impulse, the rectangle, they will not overlap. And also this term will be 0.
0
But with some Roloff, and there is always some Roloff in the practice, let's say at least, I don't know, 0, 1, there will be a small frequency range where they overlap. And where they overlap, the product will be like this. Okay? Put it into the integral and compute. So this integral is 0 for all the keys that are 2, 3, 4, and larger. For key equal to 0, you find the power, okay, which is the amplitude of the 0 frequency spectral line, because simply you find the expectation of y to the square. So for key equal to 0, we have the power. While for key equal to plus or minus 1, you have something. You have a spectral line with an amplitude. Okay? So basically, you have y. Make the square and find y to the square. Put a spectrum analyzer in this point. Put a spectrum analyzer on that point. You will find a Dirac delta at a 0 frequency, which is the power of y to the square, the expectation of y to the square. Then you will have some distributed spectrum, which is the effect of the randomness that is present into y to the square, and then you will have spectral lines at 1 over t and minus 1 over t. The amplitude of this spectral line is here, as here, is proportional to the integral of this product. So, put here a bandpass filter around 1 over t and look to the two terms with k equal to 1 and k equal to -1. The bandpass filter acts like this. At the output, you will find part of the distributed spectrum, the part that falls inside the filter, but if the filter is narrowband, that part is a power that goes to 0, and the spectral line. Let us write the spectral line. The spectral line here will be cos 2 pi t plus t0 divided by capital T 2 times, and this is the amplitude. The two deltas are the cosine, 2 times the cosine. When I come back to the time, so if I take the inverse Fourier transform of this part, this term here is the Fourier to the -1 of this part for key equal to -1 and +1. I don't care of the rest. So look only to key equal to -1 and +1. And take the inverse Fourier transform. What do you have? Two Dirac deltas, one in 1 over t, the other in -1 over t, with their amplitude and phase. The amplitude is the amplitude of the two sinusoid, and the phase is here. This is the effect of this term. And plus, there will be some eta prime, something that is